Hi, Giovanni. Thank you for inviting me. And hi, everyone. So yeah, my title is quite long, and it's also discussing exceptional points, which is something that I imagine many of you don't really know what they are. So let me first introduce them in the context of non-Hermitian systems, and then I will give you a bit more details about them. So exceptional points are points of singularities in the parameter space of non-Hermitian systems. And probably many of you are not familiar with the concept of non-Hermitian systems, or most likely you have been taught, as I was taught as well, that if you have a system and you describe it via an Hamiltonian, this Hamiltonian must be Hermitian. Now, this is true for a closed system, but whenever we try to describe an open system, an Hamiltonian does not suffice. So there are different ways to do this. For example, you could start from a master equation, and then you could take, for example, some mean field limits and end up with an effective non-Hermitian Hamiltonian. So a non-Hermitian Hamiltonian is nothing but an approximation to a far more complex dissipative-driven dynamics. But even if it's just an approximation, I will show you that it actually works really well in order to capture some phenomena in a variety of bosonic systems, or generally systems that are open. For example, photonic systems or mechanic systems or metamaterials, as I will show you in a second. And if the notion of a non-Hermitian Hamiltonian still seems very strange, let me try to repropose this concept in a different way. So usually when you have an open system, and magnetic systems are by definition open systems, you would start by using an Hermitian Hamiltonian, and then separately you would calculate, for example, with some techniques or perturbation theory, you will calculate some relaxation times that are associated with the magnetization dynamics. Now, via these non-Hermitian theories that have been really emerging only in the last, I would say, 5 to 10 years, what you aim to do is to include both this mechanism within an Hamiltonian description. And then naturally that Hamiltonian description becomes non-Hermitian. So since these are the beta spin seminar series, I imagine that you are all very familiar with the LLG equation. And let me try to convince you that this equation does actually encode a non-Hermitian Hamiltonian. So here you have a macrospin, this evolving in time according to some effective field that you're applying to the system, and I guess you all know this very well. And then in order to reproduce, for example, FMR experimental data, what we usually do is to add some dimensionless phenomenological parameter, which is called Gilbert damping. And this term just tells you that ultimately, even if your magnetization will be driven, it will eventually relax. So if you now take this equation and you perform a few quite straightforward calculations, so you look at the linear regime to start with, usually it's the simplest one, and then you call the deviation from equilibrium magnons, you can invoke Heisenberg equation of motion and recast this equation in terms of an effective Hamiltonian. So there is nothing particularly wrong that you are doing while doing so. And as you might expect, this Hamiltonian is not Hermitian. And it's really not Hermitian because this term is telling you that the number of excitations, you are now writing the Hamiltonian for the magnons. So this term is telling you that the number of magnons is not conserved. Ultimately, there is dissipation in the system that wants to minimize the number of magnons and ultimately just come back to equilibrium. So if the number of magnons is not conserved, then they are carrying energy. The energy is not conserved as well. So if you take this term and perform these few steps, you will ultimately recast a non-Hermitian Hamiltonian. Now, why do we want to do this? In the sense that everything sort of worked out pretty well up to now by separating the non-dissipative and the dissipative dynamics. So I will try to convince you that we want to do this because this allows us to have a very different perspective on the system that we are looking at. So people started looking in the last, I would say actually 5 years or less into these non-Hermitian theories. And they were mostly initially motivated by trying to understand the topology of system, whereas they become non-Hermitian. And what they realize is that through this non-Hermitian description, you can unveil phenomena or also topological phases that really do not have an Hermitian counterpart, and therefore are very interesting, are something new that we can observe in a system. There are many phenomena that are being constantly discovered. This is a very active field. So I really don't have the time to go through all of them, but let me just mention two that I think are particularly interesting. So one, it's very close to what we know from Hermitian system and has to do with topological phases. And it turns out that in some of these non-Hermitian systems, you can realize topological phases that look almost analog, almost identical to the topological phases that we know in Hermitian physics. So you end up with the real bulk spectrum. However, you can realize edge states that have a finite imaginary energy, meaning that they have a finite positive or negative lifetime. And borrowing some semantics from photonics, one will be Lasian and one will be lossy. And this leads to very interesting consequences also in the context of the nonlinear dynamics, as I will show you today. Some other effect that we have been also working on in the context of magnetic systems, but I will not discuss thoroughly today, is the skin effect. I would say that this effect is really on the opposite side of the spectrum. It's really about your system being uniquely non-Hermitian, because this effect stems from the breakdown of the bulk edge correspondence. So I think we all learned that in condensed matter theory, what we should apply to get our energy dispersion is the Bloch theorem. And the Bloch theorem relies on the fact that our bulk wave functions are delocalized in a sample, in a crystal. And it turns out that in some non-Hermitian system, this is not the case. Trying to explain this effect in dimensions higher than 1, it's really complex and it's not yet fully understood. But in 1D, it's quite simple. You can introduce some non-hermiticity by changing the likelihood, changing the symmetry between hopping from left to right and right to left, and this localizes your bulk wave functions. Now, I think someone might just wonder if these are theorist fantasies or if actually these effects can be probed. So again, this is also a very intensively active area of investigation, trying to experimentally probe non-Hermitian physics, but has been already very successful. So Lasian edge states and skin effects, exceptional points that I will introduce in a second, all these phenomena have been actually observed. The point that I want to make here is that they have not really been observed yet, at least to my knowledge, in a proper solid state platform. So they have been intensely investigated in photonic systems and, for example, in metamaterials, but their observation, for example, in magnetic systems, which seems to be, to some extent, a quite promising platform because they're always lossy, and we know also how to engineer the gain. So we know how to tune their non-hermiticity, has not been yet done. So today I will talk about exceptional points, and let me tell you a little bit what these points are. So these are points of degeneracies of an Hamiltonian systems. Turns out that there are two different points of degeneracies that we can have in an Hamiltonian system. Some points are called diabolic points. Maybe you've never heard this name, but these are actually the type of degeneracies that we are dealing with all the time. And in this kind of degeneracies, as you know, the eigenvalues become degenerate, but instead the eigenvectors do not coalesce. So your Hilbert space keeps having the same dimension. And these indeed are the usual degeneracies of Hermitian systems. But now it turns out that in non-Hermitian systems, eigenvalues and eigenvectors can both coalesce. And this is the simplest model for exceptional points. This is a coupled, a two-mode coupled system in which the two modes have the same real frequency. And now here, but there is also a coupling that I didn't include in the diagonalization between the modes. And there is also some dissipation. Now, if you plug this very simple matrix in Mathematica and you satisfy this condition, Mathematica will tell you that this matrix cannot be diagonalized and will give you an error. So what's really happening in this case is that the two eigenvectors become identical. So you lose one dimension in your Hilbert space. And you can imagine that when people figured this out and understood that this could be realized in physical systems, they were really excited because you intuitively imagine that this type of points will have characteristics that are very different from what we are used to. And one of these characteristics that is quite evident is that when you write down the response function of your system at an exceptional point, you know, when you do it at a non-exceptional point in an Hermitian system, you will find that your Green's function has a first order pole, right, at resonance. But instead, when you do it for an exceptional point, you will find a second order pole. So in few words, these exceptional points do really display and enhance sensitivity to perturbation, because their divergent-like behavior when you perturb the system around this point is much stronger than what happens in a conventional Hermitian system. So that's why people are really looking at ways to try to use this type of points to become for sensing applications. I would say that there are also, maybe from the fundamental side, even more interesting physics applications. For example, you can adiabatically go around an exceptional point in parameter space, and this will allow you to transfer a quantized amount of energy between two modes and things of this sort. Now, it turns out that exceptional point naturally emerge in the dynamics of magnetic systems. And this was realized already a few years ago by Lee and co-authors. Obviously, they have to emerge in some type of coupled dynamics. You need at least two modes to realize an exceptional point. But without going through the mathematics, let me just write here the equation of two LLG equation. This is a coupled system, coupled via some exchange. The proposal here relied on, you know, some ferromagnetic bilayer in which in the middle it doesn't have, by the way, to be ferromagnetic in principle, as I will show you in a second. And here in the middle, there is some metal, for example, mediated some RKKY type of interaction. And then these two parameters, alpha 1 and alpha 2, can be modulated. So also their sign can change depending on if you are, for example, injecting some spin current and things of this sort. And let me also stress that initially, people were always only looking at exceptional points in the context of a PT symmetric system, meaning that there is one degree of freedom is lossy, and the other one has a gain type of dynamics that is exactly balanced with the loss, meaning that here you would have an alpha 1 equal to minus alpha 2. So that's where the authors focused, and they predicted the existence of these exceptional points. And then there was an experiment in which what they did was to fabricate different heterostructures. And they started probing separately these parameters. So they start probing the frequency by FMR, start probing the broadening also by FMR. And also with a series of measurements, they start probing the RKKY coupling, and they build a different structure, varying, for example, the thickness of the platinum to mediate a different type of RKKY coupling, such that it would satisfy the exceptional point condition that I just showed you before. So nothing to take away from this measurement, but naturally looking at it, you might have a doubt that you know, every quantity has been measured indirectly, and the main assumption is that your system is really uniquely described just by these two simple equations. So by looking at this, we wonder if we could maybe push even further and try to find really a direct experimental signature of these exceptional points. So if we want to do anything interesting with them, we should at least understand where they are. And these all theories were always derived ultimately in the context of linearized dynamics, right? When you can take your Hamiltonian and reduce it to a quadratic Hamiltonian, it means that you have linearized your LLG equation. So we wanted instead to understand what was the interplay between linear and non-linear spin dynamics. We had to start somewhere. Ultimately, we have a very simple starting point. We are looking at some system, and we also want to explore non-linearities. So we are looking at easy plane magnetic system, having in mind the chromium chlorine. And we're particularly attracted also by this material because there has been a recent report that you can really change the strength of the interaction between acoustic and optical modes by applying some symmetry breaking magnetic field. So you have a further knob to really try to access this exceptional point condition experimentally. And what we do is to write down to LLG equation in which there is always some gain in, for example, the top layer and some loss. Of course, you could write some spin torque instead of this, very phenomenological description. Ultimately, you can find the same transitions that I'm going to talk about, but we wanted to keep it general for allowing for different ways of spin injection. And here there is gain in the system, but importantly, the gain is always smaller than the loss. So overall, if I would just sum these two, I would still get a lossy system. So I don't risk chaotic behaviors. So then we linearize the dynamics, and what we find are two regions with exceptional points. Here, again, I'm varying the antiferromagnetic coupling, but there are definitely other parameters that are more experimentally accessible, such as a field, that you can vary to access these points. So here, the antiferromagnetic coupling is very weak. This is an exceptional point, right? It's a degeneracy both in real energy and imaginary energy. And here, with larger antiferromagnetic coupling, there is another region encircled by exceptional point. So let's see what happens. For region 1, what we find in our simulation of the LLG equation is that if you're here, for example, and you look at this quantity is nothing else but this. So I'm really looking at the coupled dynamics. Here, due to a strong magnetic field that we are applying, the coupled dynamics is always ferromagnetic. And also, even if you're injecting some current in one of the spin, the overall dynamics is damped because your system is overall lossy and the dynamics is coupled, so it kind of self-regulates itself. But when you start crossing the exceptional point, what you find instead is that one of the macro spins will just flip. So there is you can definitely call it, I believe, a dynamical phase transition whenever you cross this point and you are in this region. This is also very easy to understand, the dynamical phase transition. So notice that we are at very, very small couplings. So what's happening here, in few words, is that at some point, each macrospin obeys its own dynamics, and one is pumped and one is lossy. So the one that is pumped would eventually switch, at least for the values of pumping that we are using. And instead here, what you see in region 2, it's quite different. Now the antiferromagnetic coupling is quite strong. And what we find is that, again, when we are here or here, still the magnetization dynamics is overall damped. But when we enter in this region by crossing the exceptional point, then we enter in a regime of very large amplitude self-oscillation. So we do this by crossing the exceptional point, but I think it's important to remark that actually this is a classical phenomenon that is known. So we realize that this exceptional point represents nothing but of bifurcation in the magnetization dynamics. Anyways, I think that these two examples connect, give the idea that exceptional points in the linearized dynamics have actually a very strong relation to dynamical phase transition in the nonlinear dynamics. And if we adopt this point of view, it might be much easier to actually identify the position of an exceptional point in a magnetic system, because this type of theory provides a direct measurement for it. And also maybe as an underlying comment, for us, it's very easy to identify where there is an exceptional point, just a matter of linearizing the dynamics. And so we can easily, through this method, identify, for example, regions in which someone can generate very large amplitude oscillations that might be ultimately even potentially useful for magnetic nano-oscillators. And let me, with the time left, which is not much, just use exceptional points as an excuse to introduce our proposal of a non-Hermitian magnetic topological phase. This will have a lot to do with what I introduced at the beginning. The fact that in some PT symmetric system where the gain is balanced with the loss, we can realize some lasing and lossy edge states. And Hermitian, so typical magnonic edge states, they've been really sought after from a theoretical point of view, but in my opinion, also in some others, there is not really yet the direct experimental observation. Neutron scattering really doesn't allow you to see these modes much because of issues of spatial resolution, and even transport experiments in which you would see, for example, a thermal Hall effect are not that easy. It's not that easy to make a one-to-one connection between the emergence of this edge state and whatever is measured. And I can comment a bit more on that if you're interested. So I'm going to make the claim that is by, and also, by the way, every magnetic system is non-Hermitian in the sense that there is always a dissipation, and in whatever Hermitian proposal, we just kind of disregard this dissipation. But I'm going to make the claim that it's really about that if we don't neglect it, and actually we exploit non-hermiticity, this is what can lead us to a clear experimental signature. Okay, so I will try to go as fast as possible through this. So our building blocks are spin torque oscillators that you have heard already today about. In our case, again, we just thought initially about this platform, and the only thing that we are interested in from a theoretical point of view, it's the possibility of injecting spin current, so create some injection of angular momentum, which will also be a non-Hermitian contribution, because in this case, you are injecting a number of magnons in the system. And we are interested in dynamics of the free layer. So that's how we thought initially about this. And recently we are talking with some experimental collaborators about realizing this in studying synthetic antiferromagnets. So we are thinking about an array of spin torque oscillators, or alternatively some multi-layer synthetic antiferromagnet in which there are metallic spacers that are mediating RKKY interaction. And I can always make this metallic spacer different, or for example, different thickness, such that this interaction between A and B will be different from the interaction between B and the A in the next unit cell. So really what I'm trying to do here is to build a system with a two unit cell, two sublattice translational symmetry. I want to do something topological, I need at least two bands. And then ultimately, what I do is to inject some spin current. We inject some spin current in A, and then we do not inject anything in B. So there will be an effective gain on the A sides and some loss on the B sides. And here we can also exactly diagonalize the system. Maybe I will not have the time to go through the details, but what happens is that there is a special region separated by this one by an exceptional point in which suddenly the bulk, even if you're injecting spin current in all these A sites, you don't see this reflected in their imaginary energy. Their imaginary energy turns out to be zero in virtue of the symmetry that this system has. But instead, this edge state here and here will have positive and negative imaginary energy. And I will show you that it's because of this positive imaginary energy that you can kind of beat this constant issue that we have with the Bose-Einstein distribution function that does not allow you to just access the edge state. But every time you try to access these edge states, for example, thermally, you're going to populate all the bulk modes below. So those will hinder your signal. So what do you expect classically in this system? I think classically, since you are injecting the same amount of spin current in all the A sites, what you naturally expect is that all these A sites will start undergoing precession. But this is not actually what happens. So again, with the minute left, let me show that we did the simulations of the full magnetization dynamics. We took 20 coupled spin torque oscillators. And what we realized is that in this PT unbroken phase, this topological phase that I was showing you before, in which the bulk states become real, now you start injecting spin in all the A sites, start running the simulation, but you don't see nothing from the bulk. So the bulk becomes dormant for a very long time, sometimes much longer time than our simulation, but instead the spin The macrospin at the edge, the one that had some magnum modes with positive imaginary energy, the lasing modes, that will start precessing. And this precession is a topologically protective microwave emission. Now, is that just a coincidence? Well, not really, because you know, when you start moving away from this topologically protected, also PT unbroken phase, you end up in this region. And here, just in this proximity, you will still see, since there is still topology, but now there is not a special type of protection that I can comment on more later, you will see the macrospin at the edge will start precessing, but then sooner, much sooner than before, all the other spins in the bulk will be activated because you're injecting spin current. And if you're very far from this phase, so here in your parameter space, you just see what you classically would have expected. So all the spins that you're injecting are precessing, and then eventually, because of nonlinear effects, you will also start seeing the others doing so. So let me conclude here. So I try to show you very quickly that the linearized dynamics of a coupled of SOT array can realize a topological non-Hermitian SSH model, and most importantly, we can actually see the signatures of topological edge state in the nonlinear dynamics. We also, in a different work, investigated some experimentally relevant perturbation. And I also discussed briefly how the exceptional point are associated intrinsically with magnetic dynamical phase transition. But I think for me, the most important takeaway is that really the inclusion of magnetic dissipation, which we often try to avoid, can actually unveil new phenomena. So if you're maybe interested in this, my colleague and I just put together some perspective and review, where we try to summarize all these effects up to now in magnetic systems. And well, thank you for your attention.